Give everybody a second to filter in. Thanks for joining us, everybody. We're going to get started in just a few seconds here. All right, we got people coming in, so I'll go ahead and get started. Thank you for joining us today for the November US MAP webinar. We're so excited to have you. My name is Harrison Dreves in the Communications Office here at NREL. I'll be running the technical side of today's webinar, and I just have about 90 seconds of housekeeping before we get started. I think a lot of you know the drill here, but everyone is muted by default. There's two options to connect to audio in Zoom. You can either listen through your computer, that's the default. It works great for most people. If you're having issues with that, you can all by phone instead. Just click that audio button, the little up arrow next to the audio button in the bottom left corner, or disconnect and reconnect to the webinar and choose the phone call option when you're joining. If you're having any issues with that audio connection or any other aspect of the webinar, please message me, the host, using the chat panel. I'll be watching that chat all webinar and will be available to help with any technical issues that come up. We want to get you connected so you can see the webinar. We are going to be recording today's webinar, and that recording will be available in a few weeks on the US MAP webinar webpage. So if you are having issues, you can always go back and watch that recording once it's available. We're also going to be doing a Q&A period at the end of today's webinar where you can ask questions of our speaker and his research. Please submit those using the Q&A panel, not the chat panel. The chat panel is for technical support. Q&A panel is for questions. So click that double speech bubble button. If you have questions, type them in at any point during the webinar, and then we're going to get to as many of those as we can at the end of the webinar. All right, with that, I'm going to introduce Ross Kerner. He's an NREL postdoc and director's fellow. He was involved with this research, and he's going to be introducing our main presenter for the day. Ross?
Thanks, Harrison. Yeah, I'm happy to introduce Barry Rand. Barry was my PhD advisor. We both got to Princeton in 2013. Barry came from IMEC before that, working on OLEDs and OPVs, and then we got into the Perovskite space. And towards the end of my PhD, we worked with Lynn Liu and Clay Hamill to get this CETO and the CETO award, and that's what Barry will be telling you about today.
Thanks, Ross. Let me bring up my laser pointer. There it is. Sorry?
Your screen looks good. Take it away.
Okay, thanks. Let me just minimize this box here. Having trouble doing with the laser pointer activated.
It's not showing on our end. You can.
I know it's not, but it's in the middle of my screen, and as long as my laser pointer is showing, apparently will not allow me to minimize that. So now I've learned that the hard way. So here we go. So some of you may have caught the not so subtle pun in the title here, looking at quote unquote solutions for perovskite solar cells and trying to delve into some ink chemistry that can exhibit change to inks as function of time, and depending on their composition can even influence the final composition of that ink and the film that you're trying to process from it. This work was not done exclusively or even primarily by me. I'd also like to acknowledge Junan Hu, who's a graduate student here at Princeton, Antoine Kahn, a collaborator, and Jeff Schwartz at Princeton's chemistry department, as well as contributions from Ross Kerner, both while he was here at Princeton, as well as currently at NREL, and Joe Barry. So an outline to the talk today. I'll start by telling you a bit about things you probably already know, which is coordination chemistry, and then talk about what happens when solvents that coordinate with these perovskite precursors in solution go wrong, and what can go wrong, and what has been observed to result from those types of interactions, and also ways that we can leverage such interactions to maybe produce films or final passivation approaches that have positive outcomes for devices. And I'd like to just give a shout out now, as well as at the close, that this presentation is almost entirely based upon results from our CETO project, with focus on important lessons for commercialization and trying to work toward stabilizing these inks as well as devices. We'll talk about things like DMSO, which is one of the early actors found to be reactive in these inks. We'll talk about amines, as they are a very common class of additive and reactive agent for films. And then the very recent results that I actually didn't have part of, but Ross and Joe did, based on impurities that are sort of intrinsic to some lead iodide sources, and then end with some conclusions. So in general, we can think about having lead iodide hanging around in solution. And when you change the stoichiometry or composition of the solution, there are numerous options that can result due to sort of equilibria of various solution species that might be around. For example, if you had lead iodide coordinated by DMF, but introduced bromide into that ink, it could be that bromide takes the place of an iodide system, or introduce DMSO to that ink, and it could be that DMSO quite likely will take place of a DMF, which had sort of equilibrated with the lead iodide hanging around in solution. And the way that these equilibria are often constructed is on the basis of hard-soft acid-base empiricism, whereby the donor number is used to sort of convey how strongly some solvent will coordinate with some species in solution. The donor number is quantified with a reference complex of antimony pentachloride, which is a hard ion. And I also think this is done in a solvent, maybe it's dichloroethane or something similar to that. And so this reference complex, it has always been sort of questionable whether this is a perfect analog to what we can expect in lead iodide and solvents such as DMF and DMSO, where lead is a semi-soft ion rather than antimony, which is a hard ion. And it's expected that lead will prefer soft interactions, meaning things like sulfur will be preferable over nitrogen, preferable over oxygen. And yet most of our solvents tend to be oxygen-rich solvents. And also preferred will likely be softer halide species like iodide over bromide over chloride. And work from Lin Liu and Jeff Schwartz and Clay Hamill, who I believe also gave a talk in this seminar series maybe some year ago or more, showed work whereby increasing donor number generally led to a change of the sort of expectation for these methyl ammonium iodide and lead iodide in solution, whereby low donor number solvents, things like acetonitrile or propylene carbonate or gamma butyrolactone, would lead to single crystal growth, basically because they didn't coordinate very strongly with the lead iodide. So the lead iodide system would come out of solution and crystallize. And then those solvents that have a sort of intermediate interaction with lead iodide, things like DMF, NMP, which are preferable for thin film processing because they properly solvate the system and once cast can be removed from the film. And then things that would be considered as additives like DMSO or DMPU, these solvents should be used sparingly and often as additives because they coordinate very strongly with the solutes and can be often difficult to extract from the final processed film. It was found later by Clay and others like Jeff Schwartz and Lin Liu and Paulette Clancy that one could more accurately quantify not using the donor number, but something analogous to it, which is basically the enthalpy change for molecules complexing to lead iodide. So you look at the change in enthalpy of lead iodide as a different ligand interacts with it. And this was more quantitative compared to the donor number. However, if I do a back and forth or put these on the same slide to more accurately represent it, you can see that most of the general interpretations and qualitative discussion here is unchanged. A few have flip-flopped modestly, but nothing dramatically. And so a lot of the donor number predictions, even though qualitative, tend to hold true. And we see that, again, we have this sort of lowly coordinating solvents which lead to crystal growth, intermediate ones that are good for principal or primary solvents, and then ones that ought to be used sparingly because they coordinate very strongly and it might be very challenging to remove these. And note that DMSO exists somewhere on the edge of this solvent to additive regime, but clearly ought to normally be used in the context of an additive and not a primary solvent. And so that's sort of my starting basis for how we select solvents. However, it should be recognized, and I think if many of you have been following the literature on perovskites, you probably already know this, that not all solvents are inert and not all additives are inert. And so we cannot exclusively rely on these metrics for solvent and additive selection. There are numerous common solvents and additives that react with perovskite precursors in solution. That means that the solution mixture does not necessarily dictate the film composition, either in terms of stoichiometry or even the materials that are incorporated, because a reaction could lead to byproducts, which may very well be replacing your expected reactant in the final perovskite film. And so a thought experiment is, I bet a lot of us produce, inks for these devices, and think about this sort of context. I have a means of casting it on a substrate, and then I anneal that substrate, and then what comes off are those solvents and those additives, and what's left behind is my perovskite film with the same stoichiometry and composition as that of the reactants that I use to make my ink. And it turns out that this notion, while I think ideal, is not the one that often plays out. And if we better understand what can come inside this processing step, then we can better confirm and sort of determine what our outcome is and lead to best results with regard to performance and stability. So I'll start out by talking about DMSO, basically because it's a system that we've done a lot with, and it's a very often employed solvent, a sort of go-to additive for making halide perovskite films. So from a very simple perspective, if you add acid to DMSO and heat it, you can expect a redox reaction to ensue. In this case, whereby something like dimethyl sulfide, methylamine, iodine, and water are created as a result. However, if we take just a solution of DMSO and MAI and heat it, we can see clearly we know that clearly iodine was created by the fact that this solution becomes very dark. But if we do NMR, we also observe formation of other cations, specifically dimethylammonium and ammonium. And these cations can be incorporated inside a perovskite film. And Lin Lu and Jeff Schwartz and Clay Hamill did some pretty careful work a few years back regarding such sort of additional reactions that can occur. And it turns out that indeed within the DMSO methylammonium ink, you can result in reactions that form byproducts like not just ammonium, but things like dimethylammonium through this sort of methyl group transfer that leads to, there it is, the dimethylammonium ink byproduct as well. And in the context of our CETO award, what we did was we incorporated these additives either through the result and action of DMSO and methylammonium being together in the same ink, or by the action of specifically alloying and introducing ammonium and dimethylammonium into an ink that was devoid of any DMSO. So we wanted to either put those byproducts in as a result of reaction or put them in overtly. And what we found was, looking now at some UPS data from Antoine Kahn. So what this is showing is the valence band. So the start of those filled states in the methylammonium, in this case, methylammonium lead iodide on titania system. And what you're looking at here, let's look at the sort of DMF, pure methylammonium lead iodide film, is the forbidden gap here in, here's the Fermi level, and then the forbidden gap, and then the start of filled states. And you can see that those filled states become more and more dense as you go further into the valence band to the tune of a couple of EeV. And in the case of using a solvent additive like NMPT, which doesn't have any of these byproduct reactions, we can see a very similar valence band maximum, that there's no introduction of any defect or gap states into this system. However, if we use DMSO, we can see that this gap, this forbidden gap, now has some states in it. And these have been introduced through the act of introducing dimethylammonium and ammonium to the film. That can be confirmed in the upper right panel here, B, where we've specifically introduced ammonium and dimethylammonium, but without any DMSO present in the ink. And we can see a similar manifestation of these gap states. Therefore, this was our sort of early entry to the fact that we really need to know what our final film composition is, and two, not all byproducts that might happen as a result of some ink chemistry are benign. It could be that some don't enter the film at all, and it could be that some, even if they do enter the film, are benign or inert. In this case, ammonium and dimethylammonium introduced into methylammonium lead iodide, we can't say that. Further on, what Clay did was to recognize that when we have the deprotonation of methylammonium through proton transfer with DMSO, the presence of methylamine, the deprotonated methylammonium, when in the same ink as formamidinium, will lead to a reaction between formamidinium and methylamine, or as generalized later, and we'll show, leads to the formation of this N-methyl formamidinium cation. It turns out that similar to unintentional incorporation of ammonium and dimethylammonium and methylammonium lead iodide, that incorporation of MFA in these mixed FA-MA devices is particularly problematic. One paper that showed this, and you can see here with the introduction of MFA, we see this device suffers considerably poorer performance compared to the device that lacks that MFA. And what this group showed was that the act of having DMSO left behind in the film upon annealing leads to this formation. This means this doesn't have to happen in the ink. This can happen as a result of having some remnant DMSO behind. The way that they alleviated this problem in this work was to employ this sort of vacuum process before and perhaps also during the annealing step to better remove DMSO from the film. In our experience, one, this vacuum process wasn't particularly amenable to upscaling and sort of commercialization pursuits, but two, that the remnant DMSO that's trapped at the bottom of the film, and folks from Jinsung Huang's group have seen a similar thing happen, that whatever's trapped in the bottom of the film tends to kind of stick around there, and it's very hard to remove. And so this annealing process wasn't necessarily a panacea that could be generally applied. So what we did in some recent work was to employ this process of hot casting. So this is a process where you elevate the temperature of a substrate as you cast the film onto it. And what it does is it promotes growth of that film rather rapidly, and also allows you to access thicker films with lower molarity solutions. So what I'm showing here in the upper left is, as a function of the substrate temperature, the thickness of the film. And I'm showing it for different molarities of solution by about almost an order of magnitude, from 1.4 molar to 0.4 molar. And what we see is that obviously higher molarity solutions lead to thicker films for a given substrate temperature, but that notably, I can use a 1.4 molar solution all the way to about a half a molar solution and still access films in this area, this sort of thickness of relevance, the 400 to 600 nanometer thick film, where all of my incident photons are nearly entirely absorbed. And I can try to make meaningful comparisons between films of similar thickness and films of sort of similar quality when looked at from the above in an SEM or looked at through X-ray diffraction patterns, which speak to the fact that all films have similar phase state at their starting point. Notably, maybe some of these lower molarity inks even have slightly higher degrees of crystallinity compared to their higher molarity relatives, but I don't think this is anything we need to dive too much into. But what we did do was we used NMR, and I'll come back to this right at the end of the talk just to sort of bookend it, to quantify what's left in the film, both before and after annealing. So you take your as cast film and then you wash it into an NMR vial cuvette, and you can then quantify the content of that film. And what we did was we first looked into quantifying the amount of DMSO that's left. And we did this by integrating and setting to 1 the formamidinium peak and comparing that to the integral of our DMSO, our remnant DMSO peak, shown here at around 2.6 parts per million. The notable aspect here is that as cast, the film with about a factor of 4 less DMSO, so about a factor of half molarity and half the additive of DMSO, has about a factor of 20 less DMSO remaining in that film. So the molarity of the solution doesn't necessarily correspond to the amount of DMSO left. And it appears really promising, the fact that we can reduce the amount of DMSO in our film by about a factor of 20. As we anneal that film, we can see clearly the amount of DMSO goes down, and it goes down more prominently for the film that had more DMSO to start with, such that the end point is not so dissimilar. It's about a factor of 3 or so between the lower molarity ink and the higher molarity ink. However, let's look in more depth at the full NMR data shown at the bottom here. Before annealing, we can see not only is DMSO left, but also DMF is there in smaller quantities. And then after 1 minute, we can see that the DMF is entirely gone, but DMSO, as we know already, is not. And the device that had the higher loading of DMSO in it, even after 1 minute, starts to reveal the presence of this MFA, this N-methylformamidinium cation, which we know to be problematic. At 40 minutes, the film with lower DMSO loading has completely eliminated the DMSO peak, but the one with higher loading of DMSO, it's not gone yet, even after 40 minutes at 120 C. And the MFA peak has notably grown. The MFA peak at this time with the lower DMSO loading is now just starting to be present, but it's also kind of like a hard sell to say it's there in considerable quantities. Showing that this leads to differences in devices, we first turn to optical techniques and photoluminescence. So turning your attention to the top panels here, what we did was monitor the steady state photoluminescence output of this perovskite film, either when excited from the top or excited from the bottom. And the reason that we did this is we were certain that the DMSO additives were almost entirely isolated to that bottom trapped interface between the substrate and the perovskite. And what we see is that the film that has the lower loading of DMSO, there's not a large discrepancy between the photoluminescence output at the top, where most of that DMSO is not present. As you can see, there's about a 10 to 20% difference, but there's about a factor of 2 difference when we illuminate the substrate through the substrate. meaning that this bottom part of the film has a considerably poorer quality when you have that DMSO trap there. And we're asserting this is due to that reaction that results in MFA production. The time resolved photoluminescence shown in the bottom shows negligible difference when excited from the top, but from the bottom we can see that the one with the DMSO trapped in there has a considerably shorter lifetime compared to the one without that considerable amount of DMSO trapped there. And so I think with these data, we can pretty confidently say that the presence of MFA is not a good thing. Regarding their initial performance, we find that, statistically, it's really hard to find very meaningful differences between a small amount of MFA being incorporated in these films and not much at all. So the device with lower molarity leads to slightly better performance on average, but I would say that they all perform pretty admirably in this device structure. However, where they really start to diverge is with regard to their stability. So in this device architecture, which is an NIP device architecture consisting of tin oxide and then the FA lead iodide system, and then a spiro layer and then a gold top contact, we see a relatively rapid burn-in over the first tens of hours of the device, followed by a relatively stable phase. And what we see is lower DMSO loading, shown here in blue, has considerably longer lifetime than the device with the remnant DMSO, which we know produces MFA. In fact, if we extrapolate the post-burn-in device with low DMSO, we get an extrapolated T80 of somewhere in the region of 5,000 to 6,000 hours, which is among the higher stability devices in literature. And so our assertion is that MFA may have more pertinent implications on stability than the initial efficiency, which of course makes it ever more challenging to try to assess which of these byproduct will be particularly damaging and which will be relatively benign and inert. In terms of screening alternatives to DMSO, while we don't have any clear-cut panacea for this, we can note definitely DMSO in presence of MAI is deleterious and leads to considerable reaction. GBL similarly will react with MAI, but NMP appears promising as not suffering from similar reactions compared to DMSO and GBL. And so we think that that there is considerable promise to further develop NMP-based inks. Now let me shift gears a little bit to the discussion of amines and reactions that can occur with perovskites. So amines are of course a rather common additive both in inks as well as a post-deposition treatment. And they have an extremely high donor number, meaning they are very likely to displace most other solvents from ligand with lead-2 in solution, even in fact iodide, where amine-based lead-2 solids have been isolated previously, which can indicate a strong affinity of that amine group with lead-2. So some of the earlier work that we did some years ago now by Ross initially was to explore lead iodide in presence of simple aliphatic amines, here butylamine. And if we take lead iodide and DMF and add butylamine to it, we can see almost instantly the formation of a cloudy solution, which turns rather turbid and dark after about a week, but that this type of solution can even be turned back toward the initial starting point by adding the equivalent acid butylammonium iodide in this case. And so this had something to do with sort of interaction between lead-2 and amines and certainly something regarding the pKa of solution. What we noticed as a sort of consequence of lead iodide interacting with amines was formation of lead zero. So where the lead iodide control remains quite stable at room temperature and under the X-ray conditions of, given by XPS, if we would expose lead iodide to solution amines, in this case butylamine, or vapor phase, in this case methylamine, or even solid state, in this case a very thin film of polyethylenamine, so a sort of polymerized primary amine on top of lead iodide, we could see a rather rapid exposure to X-rays formed lead zero, metallic lead in these systems. And I should just, as an aside, note that this lead iodide control is really quite stable, and that photolysis or even thermolysis of lead iodide to I2 and lead zero takes quite considerable heat or light to activate. And however, if we irradiate it simultaneously with heating it, we can start to see lead zero being formed rather rapidly. So just in general, it should be said that one should be very cautious of exposing lead iodide to simultaneous light and heat, because this can lead to rather rapid photolysis of lead iodide. Some other things that we should note from literature: there's a sort of well-known recipe that to produce really complete films of methylammonium lead iodide utilizing acetonitrile and methylamine. This was developed by Keita Knoll and Henry Snaith at Oxford. And they found that those inks did result in lead zero, which we now know is likely owing to some lead amide species being incorporated to the film. And what Junan did and published last year was really to isolate the exact scheme of this reaction in its entirety, and with considerable proof and comprehensive sort of analysis. Junan and Jeff really worked hard on this. And what they found was that lead iodide will, unsurprisingly, owing to the fact that amines have really strong donor numbers, coordinate. So you get this coordination complex between amines and lead-2, which forms spontaneously. The step that was underappreciated is the next one, which is the formation of the lead amide bond. And that one is photo-initiated. So the presence of a photon with the coordinated lead amine complex results in this lead nitrogen bond. And it turns out that in this type of lead amide complex, shown here in more detail in the lower left, has what's known as a beta hydrogen. So either of these carbons, beta to this amine nitrogen, have considerable hydrogen right next to them, and this hydrogen can eliminate the iodide that's bonded to lead-2 in the presence of sort of any amount of heat. This will happen spontaneously and lead to a lead imine complex, which is incredibly unstable, and so ultimately form lead zero and this Schiff base or imine product. And these products were both sort of isolated and found independently. And we found that indeed, if you have a sort of an amine coordinated to lead in the presence of light, it will lead to lead zero through this redox reaction. So that's the first step in the sort of danger of exposing lead-2 systems to amines. Now, with a little more notice to what can occur in formamidinium-based inks, it turns out that an amine will undergo an addition elimination reaction with formamidinium spontaneously, whereby this lone pair of nitrogen will attack the carbon in formamidinium and lead to the addition of the methyl group from, in this case, methylamine, to make this MFA system, and you'll eliminate and produce some byproduct ammonia in its place. So, we've already shown this MA-FA reaction above in the case where DMSO deprotonates MA. That's one way you can have methylamine around. And, also the situation with this acetonitrile alkylamine ink, it should be pretty clear that that will be incompatible with formamidinium perovskites because you'll have this instantaneous reaction. It's viable that ammonia can work, but this will only work when you've cooled ammonia down to be a liquid. And so it's not abundantly clear whether that's a completely pragmatic and realistic approach. We also find that anything else that deprotonates methylammonium in these inks will also induce this reaction. And, just published by Joe and Ross, were that impurities can also act in a similar method as DMSO does. And here are those data, whereby if you have FA, MA, here's the NMR data that shows no byproduct in this situation. This is DMSO free. And even in the case where you load that system with high purity lead iodide, we don't have the presence of MFA. However, if I introduce low purity lead iodide, we see these peaks in the NMR that can be assigned to MFA. Looking down here in the bottom is where Ross did NMR analysis of inks where he specifically spiked the solution with some impurities. And shown in black is a similar control. And the addition of water on its own did not lead to the presence of MFA and DMFA, which is interesting because that indicates that water on its own is not necessarily going to be problematic. And then the impurity that was found, lead nitrate, is also not particularly problematic to lead to a resulting MFA byproduct. However, things like lead acetate or lead oxide or systems like this hydroxyl lead impurity will lead to the formation of MFA. And that's because these types of impurities have very sort of proton accepting surfaces and will lead to the deprotonation of MA. And if you create any methylamine in the presence of formamidinium, you will make MFA as a byproduct. So what this work does, again, just published a few days ago, is it really highlights the need for proper reagent control, and that purity does indeed matter for getting results that will be sort of generally reproducible. It also tells us that inks may tolerate water if we can properly design the ink, which is important for commercialization purposes, because often doing things completely water-free is not particularly realistic. Also, but we don't necessarily have a perfect solution to this, is that methylammonium-free compositions will not be as sensitive to these deprotonation impurities as methylammonium-containing systems will be. So this work from Xuping Pang's group in China showed really generalization of these amine formamidinium reactions. You get these addition-elimination reactions with the presence of an amine and formamidinium, which lead to, the production of things like, in the case of methylamine, MFA, and the elimination of ammonia. It should also be noted that they generalized it further. In the presence of water, you can also have hydrolysis reactions that need to be very carefully considered to sort of avoid any of these happening. And they were able to show actually this sort of cold ammonia liquid was a promising approach to actual making of perovskite films with good film quality and high power conversion efficiency and stability of those devices. Very recently, work from NREL Ross and Kai and others, showed that you can actually apply amines to a formamidinium-based perovskite. Now, amines have been applied many times to methylammonium-based perovskites, whereby there is a proton exchange, and you can essentially replace surface methylammonium with some surface other ligand of your choice in this sort of 3D, 2D stack approach. But this was an interesting work in that it was an early one, or the first one, to show that you can also apply this approach of a vapor phase amine to a formamidinium perovskite. In this case, it's not a simple proton reaction, but it's this sort of addition elimination reaction, whereby in this case you're forming this cation and eliminating ammonia, which comes off as a gas. This cation is somewhat similar to the imidazolium cations that have been used, the BMIM cations that have been used in literature. And interesting analogies can be shown there. The nice thing about this work, and I think what makes it quite elegant, is that this is a sort of terminal reaction. It only happens on the surface and it doesn't propagate farther. Exposure of some primary amine to an ammonium, like a methylammonium perovskite, will not be surface terminating. It will continue to propagate through the bulk, and you can, essentially convert the entire 3D film to 2D if you're not careful and let it go too far. Also recently, work out of both Seth Marder's group as well as David Ginger's group, picked up on this interaction between amine and formamidinium. They used ethylene diamine, which, of course, if you've been listening to the last few slides, will react spontaneously with formamidinium. In this case, it leads to the formation of this imidazolinium cation as well as ammonia. And it's unclear to me whether this imidazolinium cation finds its way into the final film, or if it's just a sort of happy spectator with regard to the overall process, but it does lead to improvements in the phase stability of the final film and also to the performance of these devices. A final couple points I'd like to make is that this work does have solid state relevance as well. So many years ago, this was work published in 2016, we discovered that halide perovskites were sort of exceptionally redox active. And this work was exceedingly simple in that we mated lead halide perovskites with a readily oxidized metal, in this case, aluminum. And what we found was a spontaneous metal cation redox reaction, whereby deposition of aluminum on top of the lead halide perovskite resulted in formation of lead 0 and formation of aluminum 3+. Only at thicknesses of 50 nanometers aluminum do you start to see still the remaining metallic aluminum. Otherwise, it's all consumed in this spontaneous redox reaction, making lead 0. What we showed was some generality of this, that, one, this happens regardless of whether it's bromide or iodide, shown here with cesium lead bromide or cesium lead iodide in the case of aluminum, and also that the ammonium cation played no role in the formation of lead 0. This was really an aluminum and lead 2 redox reaction. Using other low work function metals like ytterbium and chromium naturally led to similar results. Silver, on the other hand, is an intriguing one because the presence of iodide now becomes relevant in making lead 0 formation, because it does allow this sort of redox reaction to occur at rather low stresses. Gold was another situation entirely, and I'm sort of highlighting it here for clarity. We got this wrong initially. We said this was some sort of partial charge transfer reaction in the paper in 2016, but later we corrected that, and Ross, through, I think, maybe just slower measurement compared to Lian Feng, who is so excited to see some of these results, it turns out that if you just sit there in the XPS system, that upon waiting a bit longer, the this clear feature of lead zero would emerge. So where initially you have no presence of lead zero, upon further measurement time, lead zero clearly emerges. And this is an artifact of formation of amines. And so here's the sort of cycle of that, where gold acts as a catalyst. What happens is gold attracts iodide, and it extracts iodide from the system. And when it does that, it eventually leads to the formation of HI, which goes away. And when HI is formed, it deprotonates methylammonium, and any methylamine that is formed in the presence of lead iodide will form this lead amide bond, which, as we've said, is completely unstable and will lead to the formation of lead zero. And so bringing it back around, these things are very relevant to solid state systems, but understanding interactions between lead and these acids like methylammonium and formamidinium in the presence of these solvents and other reactants and byproducts will allow us, I hope, to stabilize these systems. So a final note on the utility of NMR. I hope that, ideally that some of these measurements like EIS and space charge limited current and that we find are sort of so routine in the Perovskite community can maybe sort of start to fade away and some other measurements take their place. One that is so simple is to use NMR to quantify your final film composition. So films that are produced and the ones that are ultimately used for devices can be easily dissolved, and you can integrate each of these peaks and determine what is left behind. So here we have an FA and MA containing film, which has residual DMSO, it has residual DMF, and it also has MFA there. And so we can use this to sort of really quantify what's there in our film. And I think this type of reporting will lead to a sort of eventual maturity of this Perovskite research community. So now to return to the pun, the solutions for Perovskite commercialization. That donor number is only a single factor when considering solvent engineering. One should also consider that solvents may react, and I think I've given certain cause to be concerned and be alarmed about DMSO. Side reactions should be a primary concern, especially when subjected to the presence of DMSO and heat. And it also should be stressed that one reaction can cascade others. That is in fact what happens in the case of making MFA, which requires that initial proton transfer step with DMSO, which may have been expected, but the other one maybe was certainly more of a surprise. With regard to amines, they love lead, but they will photoreact to produce things like amides, imines, and ultimately a very problematic lead zero product. And so the main takeaway here is be very aware of irradiation during processing. Amines also will react with formamidinium. And so adding amines to any formamidinium containing ink guarantees a reaction. There's no other way to put it. But also, and a bit more subtly, is that impurities, for example, things like lead acetate or lead oxide, will catalyze these reactions because they lead to deprotonation of the organoammonium salt. And that, we can quantify, and I think we should start to quantify the composition of our film through NMR analysis. Overall, a typical solar cell has micrograms per centimeter squared of perovskite material, one that any of us make on a regular basis. When we're studying degradation, we're often looking for sort of parts per thousand of an interface reactant and trying to detect nanograms per centimeter squared of byproducts can certainly be challenging. But I hope I've convinced you that it is tractable to make progress using really standard chemical analytical techniques that are available today. And I think that through accumulation of knowledge and these types of studies, we can pave the way forward for this semiconductor technology. And with that, I'd like to thank you for your attention and give a final nod to the Department of Energy CETO office for funding this effort over the last few years. Thank you.
All right, thanks, Barry. There are a number of kind of questions that we've gotten, a number that we've also I'll highlight for people have tried to answer kind of in real time on some related topics. But I think we'll start you off on an easy one. On slide 13, the question came up, how your solar cells are typically made, and how much have you looked at, say, commercial approaches to some of those films? I think I know the answer to this, but I'll let you field it.
Yeah. So the way that these were made, so it's first the full architecture. It's an FTO substrate, so sputtered FTO on glass, and we deposit tin oxide by chemical bath deposition, and then it's a formamidinium MA based ink, which is again deposited with this, in this case, a hot casting procedure to try to minimize DMSO as much as possible. And then it's followed by the doped spirotad and the omatad and gold. So obviously that structure is not entirely commercializable, but it's also very archetypical in that we can make pretty facile comparisons of things like stability. We go here, stability to what's pretty well established in literature. And so what's pretty well established in literature is a device kind of like this. This hits 50% of its stabilized efficiency around 4,000 to 5,000 hours. And that's relatively typical, if not a bit better than typical. I should note that this is a 3,000 hours device. Now, if we want to go after a truly commercializable device, we'd want to eliminate the gold, I would argue, others would not, and also try to minimize use of spiro and things like that. We are working on that, but what we really want to do here was isolate presence or absence or near absence of DMSO to try to come to some understanding of stability or instability. And it turns out that you can still employ this incredibly simple structure and get it to live relatively long, which I think is overall very promising.
Just to add to that, were they spin coated films?
Yes, sorry.
Yeah, that's what I thought. So I guess we don't have exact data on like blade or slot die coated films, but we believe similar effects will be observed, and it's definitely being looked at.
Well, and I think that's a nice place to pivot to another one of the questions, and some of the last few kind of slides that you showed, Barry, related to kind of some of the key takeaways. So one of the questions we have here is, if you could dig into some of those kind of key takeaways, and if you put yourself in the shoes of, say, a startup, what are some of the key things that and strategies that you would essentially employ if you were a startup company to worry about some of the impacts of this chemistry in the context of trying to develop a commercial product? I know I'm asking you to put a slightly different hat on, but there are a number of questions that are kind of along that vein. So,
yeah, I mean, there are definitely really important human health reasons to avoid DMSO, but now we know that there are really important perovskite stability reasons to avoid DMSO. So I would certainly prioritize any efforts to absolutely remove DMSO from any processing scheme that's being employed, and maybe not be so overly concerned about presence of air and water, at least at this point, because they might not be of primary concern. If amines need to be employed, and I'm not suggesting that they have to be, but one should note that if methyl ammonium is used, amines are there. Like there's no way to really avoid it. The part of that ammonium salt will be at some point deprotonated during this process. And so amines are there if you're using methyl ammonium, and there's nothing you can do about it. The way to protect around those systems causing problems is to completely avoid any high energy photons around during that system being in the ink phase or processing, because that will lead to later problems with regard to devices. I would say those would be the sort of principal things I would be very concerned about from an initial point of view for a startup company.
Again, kind of, directly pivoting from kind of that last thought about, the role of having those photons around. I mean, from your perspective, at what level do you really have to worry about that photon flux, right? I mean, obviously there are essentially, say, photon-based annealing approaches that people are undertaking, for example, RTP and other things. I mean, what kind of light levels are we talking about? Is it something where, it's a concern about room lighting versus, say, an intense laser source or similar?
Yeah, I would say, yeah, if you're, that's a good follow-up question. I would say as long as your photon source is low energy photons that can still provide heat to that film, and sun's heat component still provides heat to systems that can at least absorb that light. So I would not provide any photon dose that's of the really high energy variety. So avoiding things above the gap of lead iodide, say, higher energy than green, is definitely something that should be prioritized.
Yeah, and there was another related question, in that context about UV, but I think you just kind of answered it.
UV is problematic. Yeah.
Yeah, I think you answered it. I'll also note that there have been some studies indicating some of the complications you can have even with some of your transport or transparent conducting contact layers in the context of UV, creating photocatalytic interactions. All right, another question that we got was related to kind of the location and the essentially formation dynamics that you highlighted, right, with the DMSO essentially, at that lower interface. And the question was, well, and indeed there have been some really nice work in the literature by Jinsung Wang, showing that lower interface can be defective. Mm-hmm. What's the approach to basically solving that particular problem? Is it really trying to, arrange the energy so we really can get formation at that lower interface first, or what might you speculate about that?
I think, again, it's a matter of, kind of as we show here, it's a matter of really utilizing an ink that will not lead to the formation of byproducts that are deleterious to the perovskite film. I'm not suggesting it's bad to use inks that result in byproducts. It may very well be the way forward is to utilize an ink that is somehow reactive. But when it's reactive and forms byproducts that we have identified to be bad to the film, that's where you need to sort of try to completely exclude that. And, DMSO in presence of MA and FA is certainly one.
I'll take a little bit of liberty, because I'll also note in the context of this, and as you say, right, some of these byproducts, there can also be a reaction chemistry with whatever the substrate is, right, especially in the context of some of the transport layers. And indeed, that's maybe why some of the organics are so effective at creating high efficiency devices. But yeah, really managing that defect formation is maybe the critical thing for the ink.
Sure.
In the we're wrapping up our time, so I'll check and see if Yao, who's been with us, but Silent, has got any kind of final follow-up questions that he wants to hit.
No, I just would love to thank Barry for a wonderful talk here. Real chemistry, which I always love to see.
Well, yeah, as a semiconductor physicist, I do rely on Ross and Barry for that component of a lot of the stuff, and always learn a lot. So I think given the time and in order to respect everybody's time, yeah, thanks a lot, Barry. We will be posting the presentation along with the Q&A hopefully soon. Tim Siegler's webinar, which happened a couple weeks ago, should be up on the website presently, as kind of Harrison indicated. And so with that, we'll wrap it up and thank everybody for attending.